At the end of last lecture, we were talking about the equation of state of a fluid, and that is shown on the panel on the left. We talked about the phase diagram in the pressure temperature plane. We talked about what happens when we take a fluid and compress it from the gas phase to a small volume at the constant temperature T. And at the end of the lecture, I showed you that if we examined the coexistence curve, namely the points at which the pressure stays constant as you reduce the volume. These horizontal lines up here, as I read the pressure volume isotherms, we saw that those mapped out a surface like this. If we looked in the temperature density plane, as I go down in temperature, I reach a point where now a fluid breaks up into two coexisting phases, a gas phase at low density and a liquid phase at high density. And we saw that at least I told you that the density difference between those phases as I go below the critical temperature Tc scaled as Tc minus T to the power 0.327. In other words, the same exponent that we saw for magnetic systems. So what we discovered then at the end of last lecture was that what I told you was that the critical exponents were in some sense universal. We didn't see any difference between the behavior of a magnet and the behavior of a fluid. And we're going to talk a bit more about that right now. Then I'm going to recap the other things that we did in last lecture, and then we'll go on to talk about some new material. So what we saw at the end of last lecture then was that the critical exponents seem to be, excuse me 1 second here. I want to just set my timer. Done. What we've seen then is that the critical exponents don't seem to depend on what a magnetic material is, what the magnetic material is. It seems to be the same for different systems. It doesn't seem to depend on what the atoms are either. And so this set of phenomena are called universality. So let's review for now a little bit about what magnets are, and then I'm going to talk a little bit more about scaling. So the first thing I want to mention is that we talked about the Ising model of a magnet. So what is that? The Ising model of a magnet is simply this: you have a lattice, you have I equals 1 to n, labeling sites in d dimensions. So there's n sites in d dimensions. The spins sit on the lattice sites, and they have values plus or minus 1 in some units. And when we talk about the magnetization per spin, what we're talking about is the expectation value of SI summed over n and then divided by n. Now let's just unpack this. When I write down this angle bracket, I want to mean by that a thermal expectation value, sometimes called a thermal average. That average is taken over the canonical distribution, which is usually the Boltzmann distribution. And so the formula for expectation value of something is that something itself times e to the minus beta times the Hamiltonian of the system divided by e to the minus beta Hamiltonian. Now, what I've written here is TR, which we call trace. And let me just unpack what that means. When I write down the trace of something, it may suggest to you a matrix, and indeed that's where the term comes from. But what it really means here is that you sum over all possible values of the states of the system. So let's have a look at the denominator here. That denominator we call the partition function. It's given the symbol z. And it's written what trace of e to the minus beta h means is you sum over the value of spin 1, which can be 2 states plus or minus 1, then the sum over all the values of spin 2, which can be plus or minus 1, and so on and so forth until you get to the nth spin, and its two states plus or minus 1. So that's 2 to the n possible states in all. And then you sum the values, you plug those values of the spin variables into the Hamiltonian, compute e to the minus beta h, and then add all those things up, and that gives you the partition function. Now that that's the denominator, when we write down the magnetization, as we have over here on the left screen, what we mean by that is that we take the trace of SI e to the minus beta h divided by the partition function. So here, I've just taken this expectation value of SI, so that means that if I want to compute this number, that is a number that depends on what I is. I is the label for the spin at the site I. So you choose what site you want, let's say site 17. Then you put spin 17 in here, and then you compute the sum. Now the thing about this is a trace, this sums over all possible spin values, S1, S2, S3, S17, S18, and also S25 million, right? So most of the spins, the sums of the SIs won't involve the variable S17, but some will. And if a system is an interacting system, which is what we're going to be interested in this course, then all degrees of freedom get coupled together. Now, when you compute that, then you get the curve that's shown over here. For t greater than Tc, the magnetization is 0. I'm just telling you that, but later we will prove that. And as t goes below Tc, then what happens is you get the curve shown in the pink over here. And in the first lecture, and it's mentioned on page 3 of these notes, we can make a 10 seconds theory for the behavior of m of t, and that led us to the idea that m scaled as tc minus t over tc to the power 1/2. Okay, and that's the exponent that, in fact, I told you is incorrect. In fact, the real value is about 0.32 something or other. So we're going to find out why that is later in this course. Okay, so that's the part of the magnetization as a function of temperature that you've seen before, and that's for the external field equal to 0. So over here in the picture on the left, I've written here h equals 0 just to remind you of that. Now, what we're actually interested in is what happens in the whole HT plane. This H written like this means the external field, not the Hamiltonian. That's the external magnetic field, and there's the temperature. Now, above Tc, there's no magnetization. What do we think is going to happen below Tc? Without doing any calculation, we can already see something interesting. What we would expect is that if you're near 0 temperature, then all the spins will just line up, and the fluctuations, the entropy as it were, will be very small. So very close to absolute 0, if I apply an external field in the up direction, all the spins will point up, as shown over here. On the other hand, if I'm near 0 temperature, but the external field is pointing down, then we would expect all the spins to be pointing down. So what we've just deduced is that near h equals 0 and near at low temperatures, m will be 1 if h is slightly positive, and it will be -1 if h is slightly negative. And so that means there's going to be a discontinuity in m at h equals 0, and that's designated by this sort of jagged line over here. Now, it'll turn out, and we'll see that later, that the magnetization is related to thermodynamics, the thermodynamic free energy called the Helmholtz free energy, which I'm going to assume that you've met before. So, and I'll derive this equation, but I'll assume that you've heard about free energy in your elementary statistical mechanics classes. So what that means is then for t less than Tc, the first derivative of the free energy is discontinuous at h equals 0, and this is called the first order phase transition. Now, I also want to explain the universality, that it is that the magnetization of a magnet can be something like the density in a liquid. So the idea here is a thing called a lattice gas. And the basic idea is very simple. Take a configuration of a crystal of a bunch of spins, as shown over here on the left, and let's just make the assignment that if spin is up, that means there is an atom at that site, and if the spin is down, it means there is no atom. And that means that I can map every every configuration of the spins to a configuration of atoms. So for example, this configuration here, spin up, down, up, down, down, that would look like the configuration over here of this lattice gas. And so now you can see that it may not be so surprising that there is universality between the magnet and the lattice system. Now, last time we didn't just talk about the phase diagram of a magnet and of a liquid and gas. We talked a lot about dimensional analysis and about scaling, because that's what we're trying to understand in this part of the course. So let me just remind you what we did. We talked about dimensional analysis, and the idea in dimensional analysis was that we write down the problem variables in terms of dimensionless groups. They're not unique, but we can write them down in this way. We call them pi, pi1, pi2, and so on. And then let's suppose we want to calculate some particular quantity. Its dimensionless version we'll call pi. We know that that has to be a function of other dimensionless groups, and so it has to be a function of pi1 up to pi n. And that's the only thing that dimensional analysis tells us. But the value of dimensional analysis is that it can help us reduce the number of degrees of freedom that we have to calculate. Now, just by expressing things in dimensionless groups, we have already reduced the number of potential variables that there might be in the system. And I explained an example of that last time when we talked about the shallow water waves. Now, then the second thing that we talked about last lecture was, well, if one of the variables, pi1, let's say, happens to be small, then you might say, well, we can just set it equal to 0. It's negligible. And so you might say, well, then we can just ignore that variable. And so we've reduced the number of degrees of freedom we have to think about even more. Well, that's not quite true. And we talked about two types of asymptotics. Type 1, which you might think of as common sense asymptotics, where the limit as pi1 goes to 0 is actually well defined and exists. And so we can just replace pi as some function of 0 and then pi2 up to pi n. And so we've reduced the number of degrees of freedom we have to worry about. But there's other problems where that doesn't work, and that limit is singular. And in fact, as you take the limit, pi1 goes to 0, this function will either go to 0 or to infinity. And one of the ways that this can happen is as shown over here, that as pi1 goes to 0, we can write that pi goes as pi1 to the power alpha, and then some new function of pi2 over pi1 to the alpha 2, pi3 over pi1 to the power alpha 3, and so on and so forth. And this is called intermediate asymptotics of the second kind. And I told you, without showing you why, but we'll see that in this course, that everything we're talking about in this course to do with the emergence of emergence and phase transitions, all of these phase transition problems are examples of intermediate asymptotics of the second kind. And then lastly, to recap what we just talked about, we've seen that the phase diagram of magnets has a second order phase transition, a continuous phase transition as I go below Tc, and a first order transition as I go from H being negative to H being positive, as shown over here. Okay. So then we talked about the universality. I'm not going to go through that again, and now I want to get to the new topics. So now I want to talk about what we're going to do in today's lecture. So what we're going to do in today's lecture is I'm going to introduce a specific mathematical model of a magnet, the Ising model. We'll talk about its properties, and I'm going to show you that phase transitions are impossible. We're going to talk, we're going to talk about a concept called ergodicity breaking, and we'll talk a little bit about the idea of mean field theory. So let's get started. So this I'm going to call section 1.2, and we're continuing with that. So I showed you that the magnetization behaves in a singular way, but many other variables do as well. And so I'm going to give you an example of critical behavior, and there'll be some more in the homework. So first of all, I want to talk about a thermodynamic one. I'm going to talk about the heat capacity. So the heat capacity, or the specific heat, denoted by C. So the heat capacity behaves in the following way. So it looks like this. I'm going to draw that little arrow up here to tell you that these lines go up to infinity. So what we're going to see is that the heat capacity or specific heat capacity per unit volume per degree of freedom this behaves in the following way. Near a phase transition, it goes as T minus Tc over Tc to the power minus alpha as T tends to Tc from above or below. So what I'm telling you is that various thermodynamic variables actually diverge at the phase transition, and uh, and uh, and so we want to actually understand where these divergences come from. This is obviously very singular behavior. So there's many other examples of equilibrium behavior. Now let's talk about something slightly far from equilibrium. Well, slightly far from equilibrium doesn't make much sense, does it? So why don't we just say near equilibrium? So if we're near equilibrium, so the example I'm going to talk about is the viscosity of a binary fluid. And the binary fluid is going to be near its critical point. So the binary fluid is a mixture of two fluids, and we're looking at the binary fluid just near its critical point. And if we measure the viscosity, I'm going to plot that as log of T minus Tc over Tc in logarithm of the viscosity. Then that again looks like a power law. So that's what the data look like. This is a transport coefficient. Tells you about what happens when a fluid is sheared. The heat capacity, of course, is an example of an equilibrium thermodynamic variable. And so these are some of the examples of how you can get power laws in statistical mechanics. Okay, so now I want to talk about the Ising model. So again, we're going to have our lattice like so, and then we're going to imagine that on each lattice site there is a spin variable which can either point up or down, something like that. And so I goes from 1 up to n. Si is plus or minus 1, and we are in d dimensions. And so the goal of this section then is to make understand the behavior and interacting magnetic spin system. So let's be precise about what this model is. So here is the Hamiltonian. I'm going to just write it down, and it looks like this. So let me write it down, and then I will explain to you what we mean. So this is the Hamiltonian. When I write down this over here, what that means is that I and j both go from 1 up to n, but I is not equal to j, and the I, j means nearest neighbor sites. So if I look over here, say this site and this site, those sites are nearest neighbors. This site and this site are not nearest neighbors. And so we sum only over nearest neighbors. So the idea then is that the spins have short range interactions between them. All right, so that's that. Then this J is called the exchange interaction, and it's a number that is computed from the overlap of wave functions in quantum mechanics. I'm not going to go through that, but it's an example. We will call such a thing a coupling constant. We call it that for obvious reasons. It couples together two degrees of freedom, Si and J, if I and J are on nearest neighbor sites. Then this H over here, so this is an external magnetic field. And the external magnetic field couples through the usual dipole interaction to the magnetization of the system, in other words, to the sum over spins. So we can think of J and H as being coupling constants. And we can think of these terms like sum over ISI and sum over IJ, SI, SJ. Sometimes we will call these terms local operators, meaning that they are functions of the degrees of freedom. They act in certain ways, and so we can think of the Hamiltonian as written down in a generic way. Sounds ludicrously pretentious, but a way that looks like this. I can write it as the sum of over a bunch of terms that look like this: some coupling constant, some local operator that say depends on all the degrees of freedom. And that is a sort of general way. I can think of a whole bunch of different coupling constants multiplying a whole bunch of different local operators, and that would be a particular way to write this Hamiltonian. And in this particular case here, we have theta 1 is just the sum I, J, Si, Sj. Theta 2 is are just sum over I si, and theta 3, if you had one, it might be something like sum over I j k si sj sk, for example. That could be an example. And if we had such a thing, then we would say that, in this example here, k1 is equal to j, k2 is equal to h, and k3 equals 0, because there isn't such a term in the Ising model. Now, you may think this is completely pretentious and so on, but actually this generalization of what we mean by a Hamiltonian is actually rather useful, because it's one of the things that we have to do in statistical mechanics, when we think of it in the normalization group terms. So 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 we'll try not to be pretentious for most of this course, but this is an example where it's seemingly pretentious, but in fact is actually useful, and we'll see why. Okay, now what is the goal of statistical mechanics? So what our goal is to compute the partition function. At least if you're doing equilibrium statistical mechanics. If you're doing non-equilibrium statistical mechanics, then it's much harder. We don't have a general framework like we do for equilibrium. So it's called a partition function because it is actually a function. So let's write it down. The partition function looks like this. It's a function of t. It's going to be a function of a bunch of other variables, which I'll say what they are in a minute. But let's write down what the formula is. So the formula is you sum over all degrees of freedom e to the minus beta times the Hamiltonian, which depends on all the degrees of freedom. Okay, and we know how to do that in this particular case. So in our particular case, it's going to be the sum over S1 is plus or minus 1, the sum S2 is plus or minus 1, etc., 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 up to Sn e to the minus beta times the Hamiltonian, which depends on all the SIs. And how does it depend on all the SIs? Go away. What the heck? Thank you, Zoom. Thanks so much. How does it depend on all the SIs? Well, it depends on it precisely as shown over here. It's this particular function, like so. So I've written, so this thing, as you know, is trace e to the minus beta h, as we've talked about. I've written it out this way because I want to make another point, which is that when we're summing over these variables here, these are what I call dummy variables. So you're summing over their values, and there they are inside the Hamiltonian. And so when you sum over them, then the thing that you have left is what the partition function depends upon. So first of all, we can see it's going to depend on beta. Remember, beta is 1 over kt. Boltzmann's constant times T. So the temperature is there, but what else is there? Well, we've got n degrees of freedom. So this partition function is going to depend on n, and then it depends, the Hamiltonian is written in terms of all these coupling constants over here on the left-hand side, the k's. So then what that means is that the Hamiltonian, the partition function will depend on all the coupling constants. Let's call them k nu just to be consistent. And so the partition function is a function of those coupling constants, like so. Okay, so that's the rules of statistical mechanics. That's how you compute the partition function. And why do you want to compute this? You want to compute this because if we compute the partition function, then that gives us the Helmholtz free energy. And if you look in a not very good book on statistical mechanics, it'll say, well, the Helmholtz free energy is equal to minus kbt times the logarithm of the partition function. And it's a completely true statement, but I don't think it's a very nice way to write it. And I want to write it in a much more provocative way. So I'm going to claim that there's a better way to write this. And the better way to write this is as follows. Let's start off over here with e to the minus beta h. And then what we know is that if I take the trace over all the degrees of freedom of that, then at the end of the day, I will end up with e to the minus beta times another energy, which is the free energy. Okay, so that this statement is equivalent to the f equals minus kt log z. So these two things are the same, but this is a nicer way to write it. And I'll tell you why. It's a nicer way to write it because here we're talking about the microscopic degrees of freedom. And over here, we're talking about the macroscopic degrees of freedom. In fact, there's no degrees of freedom at all. There's just the variable, the Helmholtz free energy. So this is thermodynamic, and by definition, if it's thermodynamic, it's macroscopic. Now, if you remember, we talked about how we can think about different levels of description in a physical system. And so you might say, well, suppose we could take these microscopic variables, lump them together into some other variable, then we could have a description that is valid at an intermediate scale, something in between the lattice spacing, which is microscopic, and the thermodynamic scale, which is fully macroscopic, and that's true. You can, and so you can write down an intermediate degree of an intermediate level of description, which I'm going to write mysteriously like this. And so this degree of freedom, this level of description, is going to be an intermediate level of description. And in this level of description, psi is a coarse-grained variable, which in this case some local spatial average of spins. So that's one way to think of this intermediate level of description. Another way to think about it would be, let's talk about a fluid. So I introduced this term coarse-grained level of description. And I'm going to talk about that for a fluid. Okay, so what would it be in a fluid? So if I had a fluid, I've got a box, I've got a bunch of particles bouncing around in a box. So here they all are. And my microscopic level of description, it tells me I've got particles at positions Ri with some velocities Vi, and I goes from 1 to n. So this is the position and the velocity of particles. Okay, so yeah, nothing special about that. But if I really want to think about, say, fluid mechanics, I really don't want to worry about each individual degree of freedom. So what I will do is I will draw some lines in here, and in this particular volume, in this little sub-volume, let's call it, I'll count. I'll say that there's many particles, and that means I can work out the average density. And so then I have a picture then of a fluid, which will be in terms more of its. Of course, I can't draw it very well. Its density, like so, perhaps something like that. There's its density field, and I might have a velocity field superimposed on that. I'm just drawing the velocity like this. So I've got this is the velocity vector, and the blue is the particle density. And so this would be a microscopic description. And this would be an intermediate level description. And so if I use either of these two levels of description, I should end up being getting the same thermodynamics. They're both fundamentally equivalent. And so what that means then is that at this level of description, you can ask, well, over here, you could say, well, what is the analog of the Hamiltonian? And then another thing you can ask is, well, if we have this, well, what is the analog of the trace operation? And and so I'm not going to answer those questions today, but I'm just going to tell you that over here on the left-hand side, so this thing here is called a functional integral. And this thing over here is called our effective Hamiltonian or Landau free energy. I'll just call it effective Hamiltonian for now. And we'll define what these things are, and we'll define how to compute them later. But I just want to let you know that that is something that we can construct. Okay, so now let's go on and ask ourselves, what do we mean by a phase transition? So our answer is that we compute the partition function, So the partition function, and from the partition function we get the free energy, and from the free energy we can get all the thermodynamics. So the partition function, i.e. the thermodynamics, is non-analytic as a function of its arguments. And that's what we mean by a phase transition. So if we go back to our picture of the phase transition for ordinary matter, so we have solid, and then we have liquid, and then we have a gas, then we can ask ourselves, well, these are phase boundaries, so these phase boundaries are the loci of all points where Z is non-analytic. Okay, so that's what it means. So you can say, well, okay, well that's fine. So now let's talk about the Ising model. So if we look at the Ising model, we can ask, can the partition function of the Ising model be non-analytic? Is that possible? So let's think about this. Well, we know how to construct the partition function. So the partition function is written down over here in the middle of the page on the left-hand side of the screen, and it's basically just a sum of exponentials. In fact, it's a sum of 2 to the n terms of different exponentials of a bunch of variables. So we can say then that the partition function is equal to a sum of exponentials. And those exponentials are exponentials of the coupling constants, e to the k, e to the h. And how many terms? 2 to the n terms, because there's 2 to the n different states. And since it's a sum of analytic functions, it itself is an analytic function. And so what that means is that the answer to the question is no. No. Phase transition cannot happen in the Ising model. So that's a bit of a blow, because you've just signed up for a course on phase transitions and emergence and so on. And we've just started we've just started by saying that you can't have a phase transition. So that's a bit strange. Well, let's dig into this a bit more. So we'll bear this discouraging result in mind, but let's think about this a bit more carefully. So normally what we do is we have a problem, because we normally are dealing with very large systems. So normally we will calculate the not the Helmholtz free energy itself, but the free energy per unit volume or per degree of freedom. In the Ising model, that would be n, for example. So what we expect then is that the free energy will be proportional to the system size. So we could say the volume of the system times the bulk free energy. And then there might be terms that come from the surfaces, if there are surfaces of the system boundaries. So I'll just write that for now as surface terms. And this bulk free energy is literally just defined by saying FB, excuse me, is the limit as V goes to infinity of the free energy per unit volume. Or it might be, in the case of a spin system, this might be the case in, say, a fluid. Case of a spin system, it might be FB is the limit as n goes to infinity of F over n. And I write it like this because the surface terms will go like the surface area, and that will go like, say, in 3 dimensions, the volume to the 2/3 power, or n to the 2/3 power, something like this. So if I want to extract the bulk free energy, I take the n goes to infinity limit, and then the ratio, then those terms go to 0, and I just end up with FB itself. So in fact, what we're going to see is that in order to get a phase transition, we have to take n goes to infinity. And you can see why that is the case. When we say that the partition function is the sum of exponentials of coupling constants, which are analytic, that's a sum of 2 to the n terms. If I take n goes to infinity, then it's a sum of an infinite number of terms. And the sum of an infinite number of analytic functions is a non-analytic function, or can be, whereas the sum of a finite number of analytic functions must be analytic. So in order to get a phase transition, n goes to infinity, because the sum of an infinite number of analytic functions can be non-analytic. So we will talk about this concept as the thermodynamic limit. And by that, what I mean is you take n goes to infinity, v goes to infinity, but the ratio of n over v is equal to the density, say rho, and that is fixed. And that would be what you would have if I had the thermodynamic limit for a fluid. And if I had a magnet, it would just be n go to infinity. Okay, so that's the idea that we need to take the thermodynamic limit in order to see a phase transition. Okay, so now let's talk about the classification of phase transitions. So I'm going to be talking about the bulk free energy, FB, and that we know is going to be a function of all the coupling constants in the system. I'll just write them like that. And this function is a non-analytic. So the points in coupling constant space define where FB is non-analytic that gives us the phase boundaries. Okay, so the next thing is we can ask about what are the properties of the bulk free energy. And so here I want to refer you to the book chapter, so see section 2.6 in the book, my book Lectures on Phase Transitions in Renormalization Group, for more details. But the first thing I want to tell you is that we can easy to show that FB of K is a continuous function. So you might say if it's a continuous function, how can it be non-analytic? Well, it can be non-analytic in multiple ways. So one way would be that that there is a derivative discontinuity. And that's what we call a first order transition. That's the first way. And another way that can happen is that df b by dk is continuous, but there is some other non-analyticity, such as a divergence. So, for example, we saw that with the heat capacity going as T minus Tc over Tc to the power minus alpha as T tends to Tc. So that's called a continuous phase transition. This one here is called a first order phase transition. The continuous phase transitions, that's a better term than the older term second order phase transition, which we'll sometimes see, which is due to Ehrenfest. So let me just make a comment. Ehrenfest in the about 100 years ago, he defined nth order phase transitions as dn f by dk to the n is discontinuous. So people thought then that the only thing that could happen were discontinuities, either in the function or its first derivative or its second derivatives and so on. And people didn't really know then that there could be these parallel divergences And so he classified transitions in this way, and today we know that that's not correct. So that's how he defined it. This was wrong. Um, because you can have other singularities like divergences, for example, and um, and uh, and in fact, um, his classification would work mostly uh, in what's called mean field theory, which we'll talk about. Um, in many cases. Maybe all I can't think right now if there's other cases, but anyway, that was a much too simplistic picture. So let's now talk about the specific properties of the Ising model itself. So now let's talk about that. So here is our Ising model. Um, so I'll write it for now like this: minus h is h sum over I si plus j sum over ij si sj, and then there's higher order terms which we are not going to worry about. So there could be other kinds of models, not nearest neighbor Ising models, but other models, more general Ising models with things like this. And so this part that we are actually interested in here, this we'll just call the nearest neighbor Ising model. Okay, so then we can say that the free energy of the system is minus kBt times the logarithm of the trace over the s's e to the minus beta times the Hamiltonian of all the s's, like so. So that's our free energy. Now let's work out what dF by dH is. So I promised to show you this. So let's do this. So let's ask. So my claim is that anything you want to calculate can be written as a derivative, a particular derivative of the partition function. So let's have a look. So let's have a look at, say, dF by dH. So dF by dH, so let's take the derivative of this. So first of all, you've got a logarithm, and then you've got the trace, and you've got e to the minus beta h, and you've got all this stuff in there. So we're going to ignore the we're going to ignore all of this thing here. We're just going to look at the nearest neighbor Ising model. So let's have a look at what happens when we differentiate, and we're going to be differentiating with respect to h. So that's this h over here. So the first thing that's going to happen is when you differentiate it, h is going to be multiplied by minus beta times h. So you're going to get a factor of minus kBt. That's the first term. Then you're differentiating a logarithm of something. So when you differentiate a logarithm of something, you get 1 over that thing. So then you get 1 over the trace of e to the minus beta h. So you get that. And then you get the derivative of the thing inside. The thing inside, the derivative, d by dh, just acts on this term over here. This h over si is in the middle of this exponential. So when I differentiate, it comes down to the ground level, as it were. So I just get the trace over si of what? Well, so I've got the sum over I equals 1 to n si. And then I have e to the minus beta h, like so. And then I also have a factor of 1 over kt, because when I differentiate, I bring it down here. So there's also a factor of 1 over kt, like so. So I'd like all of you, particularly if you know you haven't seen this before, I'd like you to check this. Okay, it will shouldn't take you very long, but make sure you can check that you can do that. And now you can see that the factors of kt cancel out, and then what you end up with now is minus, and then I've got the trace of the sum over isi, e to the minus beta h, divided by trace e to the minus beta h. Well, that, scoot back a couple of pages, and that, as you can see, that is just what we mean by the thermal expectation value of the thing, of the sum over Si. So I can say that this then is minus the expectation value, sum from I equals 1 to n of Si. And that, of course, is just the magnetization times n. And so now what I have is that m is equal to minus 1 over n df by dh. So if I want to compute the magnetization, I just differentiate the free energy with respect to h. And so now what does that mean for our phase diagram? Well, we saw earlier, we saw that as t goes to 0, and in fact, as t is less than tc. So let me actually write it as t is less than tc, because that's also true, that for t less than tc and h going to 0 plus or minus, there is a discontinuity in m, and we saw that right here. Here's the discontinuity. So that right over here, there's a discontinuity in M, and so that means that there is a first order phase transition for T less than Tc. Now, let me just make a remark. So this we saw this was true for t going to 0, but it's also true for t less than tc. So for why t less than tc? Well, for t less than tc, there'll be more spins, say up than down, if h is 0 plus, and it's going to be more spins down than up if h is 0 minus. Then the difference between the number of spins up and down goes to 0 as you go to the phase transition point, but there is still this discontinuity in the expectation value at the phase transition point. And so that's why there's a first order transition all the way up to TC. Okay, so that's the first thing. And this trick of differentiation is one that we're going to use a lot. So let's ask another question. Let's suppose that we made the external magnetic field spatially varying. Okay? So what that means is I started off with a uniform magnetic field, and now I've got an external magnetic field that is a function of I. I goes from 1 up to n, so my Hamiltonian would look like this. It would look like this minus the sum from I equals 1 to n, hi si minus j times the sum of I and j si sj. So that would be what my Hamiltonian would look like. And I'd like you to check for yourself that if I were then to compute df by dh, let's say hj, some particular value hj, you choose the value j, 17, let's say, then df by dh 17 is going to actually end up being minus the expectation value of sj. So you tell me what j is. I differentiate f with respect to that h, and that gives me the expectation value of the particular value sj. Okay, so that's something I want you to check, and we're going to use that later on. So I want to talk about the fact that that m is m cannot be non-zero. So the next thing we're going to talk about is the impossibility of a phase transition. Okay, so this is what we're going to do now, and we're going to see this by using arguments related to symmetry. So I want to show you a certain type of symmetry. So we're going to see that this is a consequence of symmetry. So so let's have a look at what happens. So the question we're asking is if I know the symmetries of the Hamiltonian, then what do they imply about the thermodynamics? That's the question. So let's have a look at what the symmetries of the Hamiltonian actually are. So if I write the Hamiltonian in the usual way, I'm going to just now use the spatially uniform version. So we have it like this. If we were to turn all the spins to be negative, so this we can think of as being a spin flip, or we can think of it as time reversal. There is no time in statistical mechanics. we're in equilibrium, but we can think of it as being if the spin is like this, then if we send time backwards, the spin changes sign. So this is a sort of time reversal or spin flip symmetry, and if we also uh, flip the sign of the external field, then what happens? Well, uh, the the first term has got a minus h times the sum of a minus si, so the minuses cancel out. And in the second term, each of the si's is multiplied by -1, so -1 times -1 is +1. And so what that means is that if I make this combination of two transformations, then the Hamiltonian as a function of all the spins being flipped and the external magnetic field being flipped. That is the Hamiltonian when everything was as we started. And so this is called the symmetry is a symmetry of the Hamiltonian. This is sometimes called time reversal symmetry. Or sometimes it might be called Z2 symmetry because we've permuted two objects, the spins and so on. Okay, so we have this exact symmetry, and now we're going to look at what are the consequences of it. So the strategy that we're going to do here is we're going to plug the symmetry into the partition function and see what happens. So let's see what I mean by that. So I start off with a Hamiltonian. Sorry. We'll start off with that. So now let's plug this into the partition function. So I can say, well, if I take the partition function and I reverse the sign of h, so my partition function is going to be then the sum over all the degrees of freedom. I'll write it like that. E to the minus beta h, and then minus h in here, j, and then my si's. So that's all it is. All I've done is focus on the first degree of freedom, the first term, the h. Now, remember I make this distinction about what I call dummy variables. So the spins, these are dummy variables, meaning that we sum over them. And so the answer doesn't end up depending upon them. They're like variables of integration, the integration variables. So the answers don't depend on them. And so I can now make a change of variables in this expression over here. I can write this as the sum not of the s's, the si's, but the minus si's. Why not? All I've done is make a change of variable. S goes to minus s. So these still equal plus or minus 1, or if you like, minus plus 1. And then I have e to the minus beta times the Hamiltonian. of minus h j, and then now up here I've replaced all the s's by minus themselves, which I'm allowed to do. So I've just done that, and now this is a dummy variable. Uh, so this is exactly the same thing, because of this identity here. This then is just the partition function of h, j, and t. So because this is the same thing as h of j, this is just the partition function of h, j, and t. And so what I've learned then is that f b of h, j, and t is f b, the bulk free energy, of minus h, j, and t. Okay, so basically the free energy is an even function. Okay, so that's an exact result. Okay, so that's nice. So what does it mean for the magnetization? So for the magnetization, what I've just told you is that F of H, J, and T is equal to F of minus H, J, and T. Let's not really worry about the J, so I'll just forget about that. So if that's the case, then if I differentiate it, well, I know that the magnetization as a function of the external field is equal to minus dF by dH. So we know that that's true, but I also know that f itself is an even function. So I can write this as minus h by dH. And I can write this is df minus h by d of minus h. And so this thing is then minus n times the magnetization of minus h. So what I've just proved to you is that m of h is equal to minus m of minus h. And that's an exact statement. Okay, so the magnetization is an odd function of h. So if I now set h equal to 0, then that says that m of 0 is equal to minus m of 0. And the only way that can be true is if m of 0 is equal to 0. And so what I've now proved is that exactly is that m of 0, the magnetization in 0 external field is always equal to 0 for all temperatures. And that means that there is no phase transition. So that's a bit of a shock, because that says, well, phase transitions don't seem to exist. All we've really said is that for every state in the thermal equilibrium, there is another state with all the spins reversed. And so when we average over all of the states, the magnetization cancels out. Okay, so that's very subtle, and we need to understand that. Okay, so let's try to figure out what is going on. So we already talked about how it looks like we need to take the thermodynamic limit in order to get a phase transition, because we are summing up a finite number of terms. So that's also true. So in that spirit, we can say then that we already saw that if n is less than infinity, we do not expect any non-analyticity. We do not expect so what might happen when n goes to infinity? So to answer that, I'm going to just tell you what happens, and but I'm not going to mathematically prove it for you in this lecture. But I ask you to look for this in the book if you're interested. So what we're going to see is that what might happen as n goes to infinity is that FB has the following form. So I'm going to just draw the graph, and I'll draw that, and I'll explain what I'm saying in a minute. So here is the free energy as a function of h, and my claim is that it looks something like this. Let's suppose that we have n is less than infinity, so this is an even function that is non-analytic, and so looks something like that. So this curve over here is for n less than infinity. I claim that when when n goes to infinity, what actually happens is this thing becomes like this. So it looks something like that, and right here at this point over here, right here, this is a cusp. And this makes perfect sense, because remember, we already proved that there should be a discontinuity in the first derivative of f as a function of h. We saw that just by verbally arguing. So what this, if this picture is true, then what this says is that fb as a function of h looks like this: some value fb of 0 minus something, which I'll call the spontaneous magnetization, times the absolute value of h. That term over here is the cusp, and then there's higher order terms, which I will write like this, where sigma, the exponent, is greater than 1. And then this behavior here corresponds to the following. As I take the limit as h goes to 0 plus or minus, and m is minus df B by dH, and that is equal to ms if h is greater than 0, and minus ms if h is less than 0. So what this picture tells us is that this discontinuity means that the free energy has to have this cusp, therefore it is a non-analytic function, and so that's how we get the phase transition. Now here's another very instructive way to think about this. So let me draw here the magnetization as a function of H. So here is external magnetic field, and here on the vertical axis is M. So let's first of all draw what we expect for M, for n being less than infinity, for a finite number of degrees of freedom. Well, we know that M as a function of H has to go to 0 at the origin. So here's the origin over here. So if n is less than infinity, this behavior is going to look something like this. We know as we apply a bigger and bigger magnetic field, M will eventually saturate to a value 1, and it will have some behavior that looks something like this. If I have if I have a larger value of n, so let's say now that, so let me draw this like this. So this is say n equals n1, which is less than infinity. And let's suppose now I have another value, which is like so. So in this case here, n is n2, and n2 is greater than n1, and but it's still less than infinity. So that's this curve over here. And then if I take the infinite limit, then what this is saying, so I get something like this. That's the discontinuity, and this is n equals infinity, like so. And so that's the discontinuity that we're seeing only as we take the thermodynamic limit. So okay, so that's where I'm going to stop for this lecture, and in the next lecture we're going to see how we understand this in terms of the dynamics of the system, namely in terms of what's called ergodicity braking. See you then.